last few videos, we saw how to use pins for direct problems. In the previous video, I in fact showed you how to incorporate boundary conditions. But let's now consider pins for inverse problems, which is where, in my personal opinion, the true power and genius of the Raissi approach as well as the pin approach lies. Okay, so now let us take an equation such as this. Okay, some heat addition or some other equation. You just treat it as a PDE or an ODE for now. K times d square t dx square equal to sin x. T of 0 is 15, T of 1 equal to 20. There is no problem in solving this equation provided you know K. But let us say we don't know K. Okay, so K is unknown. If K is unknown, and let's say you are within a slab, and you make a few temperature measurements. Let's say at 4 or 5 locations, you make temperature measurements, and you do get values. So let's say it is 16 here, 17 here, 18 here, 19 here, just to give you an example. I mean, I'm just making up numbers. So let's say we make these measurements. We have also measured the boundary condition, and we want to make an estimate for K. So the question is, can we estimate K now without, here is the catch, either having an analytical solution or a surrogate model. Now, what do I mean by this? Suppose I have an analytical solution. Let's say the actual analytical solution for this happens to be t equal to, let us say, minus sin x or something of that sort. Okay. Then you do the standard thing. You put that analytical model, put it in your forward model. You never bother about the differential equation now. You have a t hat, and then you take these measurements, and then it's a standard inverse problem with some model for the temperature. You know that t equal to W0 plus W1 sin x, then you can just solve it for W0 and W1. But we don't have an analytical solution dependent on K. Now, we don't have a surrogate model for the forward solution also, and you are not able to solve using CFD. Here is where pin is very helpful. So the pin solution works as follows. The pin solution is, assume that t hat of x is a neural network. And this neural network has some weights. Okay, I'm going to call it W vector. Okay, so assume that that's the neural network. Assume that K has some initial value. What do I mean by initial value? I'm taking an initial guess. Let's say K initial guess is 15 watt per meter Kelvin. Again, assume W vector has some initial guesses. This is as usual. So W0, W1, etc. You make some guesses for their values. Okay. Now we have to improve by gradient descent. Correct? We have no other go other than to improve by gradient descent. But how are we going to improve by gradient descent? We already have t hat is neural network of x, W. Do a forward prop with the given value of W. This gives you some t hat. It also gives you some d square t hat dx square, as we saw earlier, minus a k d square t dx square minus sin x. Okay, so this is, of course, our JPDE or JODE. Square it, add it for all the points. Okay, 1 by m as usual. Now notice this k is our guessed value of k, and within this d square t dx square lie our guessed values of W. Okay. X is, of course, known because we are guessing at specific x's. Okay. So which x's should we guess at? We guess everywhere in between for PDE loss, but this is J has three components now. JPDE can be any point in the domain. Why? Because PDE is satisfied at every point in the domain. Now, at these points, we still need the value of K for this loss. K is from the guessed value. Okay. So really nothing has changed from our usual pin, except that you have a new parameter K, which you are guessing for. Then you also have your boundary condition losses, which of course is the same as before. This will be T hat 0 minus 15 square plus T hat at 1 minus 20 square. So that's also straightforward. Now the final part is J data or J experiment. Now what is this? We had these 4 points where we measured the temperature. Now the measured temperature is something, and our hypothesis function will say that the temperature is something else. So we need to make sure that the difference between these two is reduced to as little as possible. So for example, we would add, this would be, temperature at all the experimental points minus the actual, I shouldn't call it experimental points, I'll just call it T hat I minus Ti square, where I are all the experimental points. So let's look at this loss function once more. J is made up of 3 parts. First part is the pure physics part. The pure physics part can be any point in the domain. You can just choose as many points as you want. You can choose 1,000, 10,000, 1,000,000. The choice is yours. The more you add, obviously, the more computation you spend in finding out JPD. But you can find out any point in the domain. But the catch here, which is different from the initial forward pass that we did in the last 3 videos, is this K is part of the iteration. So you have to start with an initial guess for K. That's fine. Calculate this through the neural network. This is, of course, known. Boundary conditions are given in the problem. Whether it's a function boundary condition or a derivative boundary condition, you can easily apply it. T hat 0 minus 15, T hat 0 minus T hat 1 minus 20, square and add. Finally, you have to look at the fact that some extra information has been given, which is the experimental values. This is what determines the inverse problem. So you ensure that the prediction you're making with your neural network matches the experimental as close as possible. So you have these 3 losses. That's fine. Now, what do you need to update? We need to update W, but we also need to update K. We can update W easily. W is W minus del J del W multiplied by alpha, gradient descent. Now, what do we do about K? Turns out K is very straightforward too. K equal to K minus alpha del J del K. This is also gradient descent. So now notice the beauty of this system, which is that here W were the parameters of the neural network and K is the parameter which sits in the PDE. But as far as gradient descent is concerned, these two are not different. They are just parameters. So you update these W as W minus alpha del J del W and K you update as K minus alpha del J del K. Really, nothing really is different as far as the neural network is concerned. In fact, Raissi and Karniadakis, as I'll show you shortly, they just put the same usual neural network algorithms and it just works like a charm. Okay, so the entire process is such that the inverse solution is baked into the forward solution. What do I mean by that? Notice that when you want to solve this problem, if I want to solve this problem traditionally, and somebody gave you this problem and said, solve it, and I will not tell you K, there is no way you can solve it. Okay, you can't solve it. Here too, you can't solve it, but you solve it as if you knew a value of K, you solve it. The next guess for K depends on what the solution was, okay, for this guessed value of k. So everything is incorporated simultaneously, which is really, really elegant. I mean, it's really a pretty way of solving the whole problem. So what you do is, unlike the surrogate model approach, the surrogate model approach will be, okay, I will guess one value of k, solve this problem, guess another value of k, solve this problem, guess a third value of k, solve this problem, solve this for 200 values, as I showed you in the first video in this series. Then basically have a correlation between temperature distribution and k, make a neural network for that. After that, when I give you new temperature measurements, then you see which k fits amongst all these simulations that you did. You solve that using a genetic algorithm. This one is much simpler. Guess a k, guess a temperature distribution. Next iteration, improve temperature distribution, improve k also. Based on what? Based on 3 pieces of data. I know the boundary condition. I know, so that is one piece of data. I know that the physics should satisfy this equation everywhere in the middle. That is this loss, JPDE loss, JBC loss. And the third and final part is the experimental data that we collected. Notice that all 3 feed towards this gradient. So when k is updated based on, for this k was the PD satisfied, for this k was the BC satisfied, and for this k was the experimental value satisfied. Similarly, W looks at, is the PD satisfied, is the BC satisfied, is the experimental value satisfied. Now, all 3 are updated simultaneously. There is no other method like this prior to this pin method in the literature. So what I would like to show you, as I promised in the previous video, is to show some of these seminal papers shortly. So please just look at the papers that I'll be showing in a minute or so. So the first paper I wish to show you was this a seminal paper called Artificial Neural Networks, ANNs for Solving ODE and PDEs by Lagaris et al. This is a professor in Greece. The paper was published in 1997. It took a good 21, 22 years for it to sort of get incorporated into the modern framework by Raissi and Karniadakis. So you can see this talks about how it incorporates initial and boundary value problems using artificial neural networks. You can also see this trial function is written as a function of 2 parts. This is not the same as the Raissi approach. These 2 parts, one part satisfies the boundary condition exactly, whereas in the Raissi thing, everything is satisfied in the least square sense, and this contains no adjustable parameters. The second part is just the PD. Okay, it only contains the PDs. Okay, so I'll just show you their approach. Their notation is a little bit different. You can see this is the equivalent of our n here. They just write it, and psi is the equivalent of our t or our u, whichever function we are trying to solve. You write the whole equation as something equal to 0, and they write it as 2 parts. This part satisfies the BCs exactly. Okay, so that's different from what happens in Raissi. This part is for the PDE or the ODE, okay, while not affecting this. Okay, so this is a very clever construction which sits there, but overall, the Raissi approach is easier to apply for general problems, even though it is less adjustable for various equations. So you can see this, it looks a little bit complicated, but the idea is very simple. If you have this equation, you would turn it into, you can see, d psi dx minus f the whole square. Okay, so that is basically the loss function. This, on the other hand, the boundary condition is ensured to be satisfied exactly. Here, x is an initial value problem, so this is like time. So they satisfy it in a exact way. So you can see they do this construction of, as I told you, x into 1 minus x, etc. So this is in order to satisfy a boundary value problem where you have a Dirichlet boundary condition and a Neumann boundary condition on the right-hand side, and they have several special constructions. Now, they deal with, as you can see, Laplace equation, an example which I also gave you. Once again, you will see a special function construction in order to make the boundary conditions satisfied exactly. So BCs are exactly satisfied. Incidentally, this paper you can search for on Archive and Google, and you will obtain it regardless of whether you are within an educational institution or not. Now, again, notice the function. The function is, since it was originally del square psi equal to f of x, f of xy, now you can see del square psi minus f of xy whole square is minimized, and you take some points. These are the PDE loss points within the domain. So they satisfy this, and they have taken a sigmoid neuron. You can see that the Lagaris paper is a shallow network, just one hidden layer with 10 hidden units, and they get very good results with that. This is, of course, please remember, 1997. Computational power, etc., was not that time. Now, with this, they solve an impressive series of problems. You can see quite a complicated ODE. You can't, they have an analytical solution here, and they compare with it. Another ODE here. These are first order ODEs. Then you have a second order ODE. Then they, of course, satisfy coupled first order ODEs, which is very impressive. And then they look at PDEs. Okay, so all these are solved here, a whole bunch of ODEs. So exact solutions here. I want to show you something which helps you visualize what is happening. So look at the final solution of the problem. Okay, so this is solution accuracy. Let's say the solution of the problem is this. When we say that t hat xy is this, what we mean is t hat is a neural network that when you take in x and y, that outputs this function. This entire function is outputted by this. So this is t hat xy. Let's say this is x and this is y. Okay, so the output is t hat of x of y. Regardless of whether it's a neural network or not, it is simply an analytical function. I have probably said this 100 times, but despite me saying it, usually in classes, I find that people miss this simple point. Okay. And what was the data? There was no data other than the boundary conditions. The boundary conditions were used, and the other information piece that was used is PD is satisfied everywhere within the domain. Okay. So whether you look at this function, so this is again a solution accuracy function, or this function, this is again t hat xy. What enables our neural network to do this is that if I change w, one of the shapes will look like this. If I change w, the other shape will look like this. So it's the universality of our neural networks that allows us to do this with the Lagaris approach. Now, what I want to show you also is the other seminal paper. You can see this is 2019. You can see now that they are solving both forward as well as inverse problems. As I said, this, apart from being the important point of our course, also is a really seminal contribution as far as this paper is concerned. Just a small change about Lagaris' idea, but sometimes small changes can lead to very profound effects. So that is what is being done here. You can see that they talk about supervised learning tasks, but they are adding physics. The way they look at it is some experimental data is given, as well as a certain amount of physics is known. So they define the governing equation this way. Let's say it's an unsteady problem or a time-dependent problem. So t here is time. So just to give you an example, you could have something like ut. You could have an advection equation, ut plus, let's say, a del u del x equal to 0. In that case, if you look at n simply is an operator which is a del u del x. Okay. So n could in general be a non-linear operator. For example, as we will see later, you can have Burger's equation where you have a non-linear term. So for example, here is Burger's equation where you have ux minus uxx. I will show you that equation shortly. So all they have is a simple method, just like the Lagaris method, which satisfies this at one shot. What we are doing, of course, is we are saying that you have the operator f. This is f here is not a function. It's an operator. Operator meaning it takes a function and returns another sort of function. So it takes u and it returns del u del t plus n of u. And here is what they have. They have the same idea that I told you. The least square loss, J, equal to J at the experimental points or J at what they call the U points or the data points, plus J where we impose the physics, which is through the PDE. So wherever you know the experimental measurements or the computational measurements already, you can see this is the ground truth and your network returns this. Okay. So similarly, this is simply calculated from the network by differentiation. Okay. So as they mentioned here, MSU corresponds to initial data, boundary data, and any experimental data that you have. MSEF is basically where you have physics. So these points where we impose them are sometimes called collocation points. Here they have, like they have said, that even though this has been observed in previous studies, they are now using modern computational tools such as TensorFlow and other things. Again, if time permits, I would like to show you an entire code for this using MATLAB in the next week. Okay. So they have several examples here. One of these examples, let me show you the results. They actually show the Schrodinger equation also. But looks like a complicated equation. So now one beautiful thing about this entire process is you don't need to put much effort to create an entire mesh or anything of that sort. You just throw points here and there, ensure the boundary conditions and initial conditions are satisfied. For example, if you want to satisfy this, all you will say is ht comma minus 5 minus ht comma 5 square. You add this to one j boundary condition loss. Okay, you can add this as saying h0 comma x minus 2 secant h x square. You see how simple it is. All you need to do is this square, this will be added to the JPDE loss. Okay, none of us know, or in case you do not know Schrodinger's equation, you need not worry. It works exactly in the same way. So here it is. They have some solutions. They have given these data points, which are basically at the boundary and initial conditions. So they serve just like the usual thing, and you get a full solution here of Schrodinger equation, which is apparently really good. Okay. So I'm not going to show you the discrete time models here. I want to show you the Burger's equation solutions. Okay. So here is one interesting example of an inverse problem that they did. Okay. So here is an inverse problem. They have a cylinder, vortex shedding cylinder at a particular Reynolds number, RE equal to 100. So now what they have is they made a lot of measurements in the entire domain. They just have points, let's say they're coming from PIV or some such experimental measurements. Now, unlike what we did with the surrogate model approach, which I showed you as the first video in the series, all they did was you measure U, you measure V, and you put in the Navier-Stokes equations. And you put in the Navier-Stokes equations and, you serve it this way. Suppose the Navier-Stokes equations, let me just write it here, is UT minus UUX, UT plus UUX plus VUY equal to minus PX plus mu del square U. Some of you might remember this. If you don't, it doesn't matter. You have a complicated equation. Okay, so this is just the U momentum equation. All you need to do is say UT plus UUX plus VUY plus Px minus mu del square U, calculate this, square it, and this should be minimized. Okay. Very simple idea. You take a guess for U, you take a guess for V. They do this using the streamline vorticity formulation. It will take us too far away to discuss that. But you do anything of this sort. This is a simple measurement, and then ensure that J equal to JPDE plus J boundary condition plus J experimental data. Minimize this. Now, what was the inverse problem they were solving? In some cases, you can try and find out what this mu is. Okay. You can actually solve for mu by looking at a field. Okay. All these inverse problems can be solved with this nice approach. They also had some nice Burger's equation solutions, which yeah, here it is. So Burger's equation, this equation is ut, it's a one-dimensional equation equal to, mu times uxx or nu times uxx. So you can solve both forward and inverse problems here. You can see this nice, sharp solutions. Again, the same thing. You basically just say U is a neural network of X and T. So take X, T, put a neural network here. It gives out U, or you can say U hat. And after that, all you need to do is say, okay, minimize JPDE plus JBC plus J initial conditions. So notice there is data given here. Initial condition is for all X for T equal to 0. This is left side X equal to 0 for all T. Right hand side, nothing is given. And on the top, you have some other conditions. So you can give all sorts of data points and just ensure that this summation is minimized. The weights of the neural network W are updated as usual. W equal to W minus alpha del J del W. Keep on updating it. You get the final set of W. You just plot this here and you get a very nice, elegant solution to this problem. Now, this tended to have certain problems. And I'll just briefly end this section of how inverse problems as well as forward problems are solved using a couple of papers that were published in by a PhD student at IIT Madras, Vikas Dwivedi. This is a good paper called Physics Informed Extreme Learning Machine. The idea was use a shallow network. And this is called an ELM structure. You fix the weights here, but change the weights at the output. And it turns out that this works really well for linear equations. So we were able to solve for fairly complex domains very quickly. PIN tends to be a little bit slow otherwise compared to conventional methods. So even in points like this, you can simply put points around. As you can see, this is a map of Australia and this is a star. Usually if any of you are familiar with finite difference or finite volume, you actually need good meshing here, whereas PIN does not require any meshing. Another idea by the same student who is now, of course, finished his PhD was to use distributed learning machines, which is somewhat similar to using a mesh. That is, you use different neural networks in different domains. Okay, so you use one neural network here, one other neural network here, so on and so forth. And they added an extra interface term. So you will see this here. If this is a linear equation, we have one such equation sitting within your assignment also. So you'll see this is distributed. You can also do time marching step by step from one step to the other. Again, this is not going to come in the exam or in the assignment. This is just to show you some advances that have happened here, and maybe some of these advances might be obvious to you. So typically, as is shown here, J is usually the PDE loss plus some regularization loss, and we add it at the interfaces to ensure some continuity. So overall, the PIN approach, unlike the surrogate model approach or unlike the usual forward model approach that we have seen so far, lets you solve inverse problems in one shot. It solves inverse problem as well as forward problem in one shot, as I showed you earlier on in this video. So the method is extremely powerful, and I expect it is going to become even more powerful in the years to come. So I hope you found this discussion on physics-informed neural networks over these last 3-4 videos useful. Please do let me know in the forum in case you have some questions. Since it's a research topic, some of what I said might not be particularly or always clear. So I'll be happy to answer those questions. Otherwise, I'll see you in the next week. Thank you.